There is a sequence of integers defined by a formula simple enough to write on a single line, for which mathematicians have found exactly 5 examples. 5. After 385 years of searching, after computer programs that have tested numbers with millions of digits, the count is still 5. All 5 were known by 1640. The first one is 3. The second is 5. The third is 17. The fourth is 257. The fifth is 65,537. They were found by Pierre de Fermat, working in his spare time by hand. Since then, in 385 years, nothing. We do not know if a sixth exists. Heuristic arguments predict that it does not, but we cannot prove it. The next candidate that anyone could possibly check is a number with more than 2.5 billion decimal digits. These are called the Fermat primes. The property that defines them sits at the intersection of 3 areas of mathematics: a 1640 conjecture that turned out to be false, an elegant 19th century primality test, and a theorem proved by an 18-year-old Carl Friedrich Gauss that quietly determined exactly which regular polygons can be built with nothing but a compass and a straight edge. This is the story of 5 numbers that Fermat believed would be infinitely many, and of the discovery that turned them from a failed conjecture into the gatekeepers of perfect geometric construction. Here is the formula Fermat wrote down. For each non-negative integer n, define f sub n as 2 raised to the 2 to the n plus 1. The exponent is itself an exponential of 2, so you get a tower. Plug in n equals 0. The inner exponent is 2 to the 0, which is 1. So f sub 0 is 2 to the 1 plus 1, which is 3. Plug in n equals 1. 2 to the 2 is 4. So f sub 1 is 2 to the 2 plus 1 equals 5. Plug in n equals 2. 2 to the 4 is 16. F sub 2 is 2 to the 16 plus 1. Wait, let me restate. 2 to the 2 squared plus 1. That's 2 to the 4 plus 1 equals 17. Plug in n equals 3. 2 to the 8 plus 1. 256 plus 1, 257. Plug in n equals 4. 2 to the 16 plus 1. 65,536 plus 1. 65,537. All 5 are prime. 3, 5, 17, 257, 65,537. Anyone can check the first 4 by trial division in a minute. The 5th is harder, but it can still be done by hand if you are patient and careful. So far, every Fermat number Fermat could compute was prime. He extrapolated. In 1640, in a letter to a friend named Leonhard Euler, Fermat wrote down his observation. He had checked the first 5 Fermat numbers. Every one was prime. He concluded that all of them are prime. He went further. He wrote that this was a proven fact, but that he did not have the proof in his head at the moment, and so he was leaving it for someone else to write down. This is, by the way, the same Fermat who later wrote the most famous note in the history of mathematics, that he had a marvelous proof of his last theorem, but the margin was too small to contain it. Fermat had a habit of declaring proofs he did not actually possess. Some of them turned out to be true, some turned out to be false. The Fermat primes conjecture is one of the false ones. But to see why, you have to know what comes next. The next Fermat number is f sub 5, 2 raised to the 2 to the 5, plus 1, 2 to the 32 plus 1. The number is 4,294,967,297. For 92 years, this number sat there. Nobody knew if it was prime. Fermat had not factored it. He had not even tested it carefully. He had just declared the pattern would continue. In 1732, Leonhard Euler took on the problem. Euler was 25 years old, working in St. Petersburg, and already changing the shape of mathematics. He turned his attention to Fermat's 5th number, and he did something that in retrospect looks miraculous. He proved that any prime factor of f sub 5 must have a very specific form. It has to be of the form 64k plus 1, where k is some integer. This restricts the search enormously. Instead of testing every prime up to the square root of 4 billion, which would be tens of thousands of candidates, Euler had to test only primes of the form 64k plus 1. Plugging in k equals 1 gives 65, not prime. Plugging in k equals 2 gives 129, not prime. Then 193, 257, 321, 385, 449, 513, 577, 641, prime. He divided 4,294,967,297 divided by 641 gives exactly 6,700,417 with no remainder. F sub 5 is not prime. It factors as 641 times 6,700,417. Both of those factors are prime. The decomposition is unique. Fermat had been wrong. The conjecture died on the very first number he could not personally check. After Euler, mathematicians went looking for more Fermat primes. Or rather, they went looking for any Fermat number that might be prime. In 1880, a French mathematician named Fortuné Landry factored f sub 6. F sub 6 equals 2 to the 64 plus 1, about 18 quintillion. Landry showed it factors as 274,177 times 67,280,421,310,721. F sub 6 is composite. In 1970, Michael Morrison and John Brillhart factored f sub 7 using a new method called continued fraction factorization. F sub 7 is composite. In 1980, Richard Brent and John Pollard cracked f sub 8 using Pollard's row method, a Monte Carlo factorization algorithm Pollard had developed a few years earlier. F sub 8 is composite. Through the 1990s, f sub 9, f sub 10, and f sub 11 all fell. Each one was attacked with the most powerful factoring techniques of the era. Each one turned out to be composite. The pattern was unmistakable. Every Fermat number anyone checked, beyond f sub 4, was composite. Today, f sub 5 through f sub 32 are all known to be composite. For f sub 33 and beyond, we cannot yet test directly because the numbers are too astronomically large. F sub 33 has more than 2.5 billion decimal digits. Writing it down is a feat in itself, but it has not been proven prime either. So the question of whether there is a sixth Fermat prime, for some very large n that we cannot yet reach, is technically open. In 1877, the French mathematician Théophile Pépin found an extraordinary primality test specifically for Fermat numbers. Pépin's theorem states the following. For any n greater than or equal to 1, f sub n is prime if and only if 3 raised to the power f sub n minus 1 over 2, taken modulo f sub n, gives the result -1. Read that statement again. It is an if and only if. It is a complete test. You compute one modular exponentiation. If you get -1, the Fermat number is prime. If you get anything else, it is composite. For small n, the test is trivial to verify. For f sub 4 equals 65,537, 3 raised to 2 to the 15th, modulo 65,537, indeed comes out to -1, confirming that f sub 4 is prime. For larger n, the test becomes computationally expensive. Computing the modular exponentiation requires roughly 2 to the n successive squarings modulo f sub n. For f sub 24, that is about 16 million squarings of a 5 million digit number. The last Pépin's test ever completed was for f sub 24 by Crandall, Mayer, and Papadopoulos in 1999. It took weeks of computation. Beyond f sub 24, full Pépin testing has been out of reach. For f sub 25 through f sub 32, we know the numbers are composite because researchers have managed to find small prime factors directly, using specialized sievers. These searches do not need to handle the full Fermat number. They only test divisibility by candidates of a specific form. Combined with Pépin testing for smaller n, this is how the entire range f sub 5 through f sub 32 has been settled. Pépin's test is one of the most elegant theorems in elementary number theory, and in the 148 years since Pépin proved it, it has not produced a single new Fermat prime. Here is the part of the story that elevates the Fermat primes from a curiosity to something profound. On March 30th, 1796, an 18-year-old Carl Friedrich Gauss wrote in his diary that he had discovered how to construct a regular 17-sided polygon using only a compass and a straight edge. For 2,000 years, the regular polygons people knew how to construct were limited. The Greeks could do 3, 4, 5, and 6 sides, and any polygon obtained by doubling sides or combining a 3-gon with a 5-gon. That was it. No new constructible polygon had been discovered since the time of Euclid. Gauss did not just construct the 17-gon. He proved that a regular n-sided polygon is constructible with compass and straight edge if n is a power of 2 times a product of distinct Fermat primes. Pierre Wonsel proved the converse in 1837, completing what is now called the Gauss-Wonsel theorem. Together they give an if and only if. So the constructible polygons are 3 sides, 4 sides, 5 sides, 6 sides, 8 sides, 10 sides, 12 sides, 15 sides, 16 sides, 17 sides, 20 sides, 24, 30, 32, 34, and so on. The prime building blocks are the Fermat primes: 3, 5, 17, 257, and 65,537. A regular 257-gon is constructible. A regular 65,537-gon is constructible. In 1894, the mathematician Johann Hermes completed an explicit construction for the 65,537-gon after spending more than a decade on it. His manuscript runs about 200 pages and lives in a trunk at the University of Göttingen. And here is the deepest point. If there are no more Fermat primes, if the 5 we know are the entire list, then the list of constructible polygons is closed. We know all of them, forever. The geometry of the compass and straight edge is finite, and the Fermat primes are what determine its limit. Gauss was so proud of the 17-gon discovery that he asked for it to be carved on his tombstone. The stonemason allegedly refused, on the grounds that the carving would look indistinguishable from a circle. The empirical evidence against more Fermat primes is overwhelming. Every Fermat number from f sub 5 through f sub 32 is known to be composite. That covers numbers with up to about 1 billion digits. None of them are prime. There is also a theoretical reason to expect that no more Fermat primes exist. It is a heuristic, not a proof, but it is hard to argue with. Treat the Fermat numbers as a random sequence of integers, with each f sub n behaving like a number of its size. The prime number theorem tells us that a random integer n is prime with probability roughly 1 over the natural logarithm of n. For f sub n, the natural logarithm is 2 to the n times the natural logarithm of 2, which grows extremely fast. If you sum these expected prime probabilities across all n, you get a finite total. Specifically, the expected number of Fermat primes is approximately 2 divided by the natural logarithm of 2, which equals about 2.9. We already have 5 Fermat primes. That is more than the heuristic expected. But the expected number beyond f sub 4 is essentially 0, about 0.09. The numbers grow so fast that the probability of any of them being prime drops below any meaningful threshold within a few terms. So the heuristic prediction is, there are no more Fermat primes. The list of 5 we know is almost certainly the complete list. This is not a proof. It is a probabilistic argument that treats Fermat numbers as if they were random. They are not random. They have structure. But that structure has not, so far, produced any further primes. And the heuristic argument captures the overwhelming reason that we expect none. 3, 5, 17, 257, 65,537. 385 years of searching, computational power that Fermat could not have imagined, algorithms that Euler would have envied, distributed networks of computers running Pépin's test on numbers with billions of digits. And the answer remains the same 5 numbers. We cannot prove the list is complete. We may never be able to prove it. The sequence of Fermat numbers extends infinitely, and the techniques we have available diminish in power as the numbers grow. But the consensus, based on heuristics and almost 4 centuries of failure to find another, is that these 5 are it forever. What makes these 5 numbers special is not their arithmetic, although that is striking. It is their geometry. Each one tells you a regular polygon that you can build, exactly, with a compass and an unmarked ruler, 3 sides, 5 sides, 17 sides, 257 sides, 65,537 sides, and combinations of those primes with powers of 2, and only those. The constructible polygons are, in a sense, the natural shapes of the universe, the figures the most primitive geometric tools can produce exactly, and the Fermat primes are the gatekeepers of that list. Fermat wrote down 5 numbers in 1640 and got the wrong conjecture, but the 5 numbers he found turned out to be more important than he had any way to know. They define the geometry of perfect construction. They probably exhaust it. 3, 5, 17, 257, 65,537. 5 numbers, the complete list of Fermat primes that humanity will ever know.